We're going to look at section 8.3, the inverse of a square matrix. So in the last section we looked at what happens if I have an equation with real numbers, the equation ax is equal to b. So of course when we're solving for x, we want to multiply each side by what we call a inverse. So the a to the negative 1 is a inverse as long as it's not equal to 1. And so mathematically, we see here, if we multiply a inverse by both sides of the equation, we know that this a inverse is what we call the multiplicative inverse. So when I multiply a number by its inverse, I just get 1. And of course 1 times x is x, so we get this x is equal to a inverse b. So again, this is our multiplicative inverse. And now we want to look at the inverse of a matrix. It is similar to that we would do with a real number. So the definition of an inverse of a square matrix is we want to have an inverse, we must have an n by n, or in other words, a square matrix. So if we have an n by n, which is a square matrix, and let I sub n be the n by n identity matrix, then we're going to call this here our A inverse. Not a to the negative 1, but A inverse. And we have a property that says if I multiply A times its inverse, I should get the identity matrix. And if I multiply A inverse times A, I should also get the identity matrix. If it holds in both directions, we must check both directions, then we say that this is the inverse of the matrix A. So let's look at an example. We want to show that this matrix B is the inverse of the given matrix A. To do so, I must show that A times B is equal to the I2 identity matrix as well as B times A. So, multiplying using the multiplication of matrices that we learned in section 8.2, we get this matrix here, which indeed equals the identity matrix I2. But we can't stop there. We must do the other direction also. We must check to make sure that B times A also equals the identity matrix. Doing the matrix algebra on this, we also see that it is equal to the identity matrix. And so here, since A times B is equal to B times A, which is the identity matrix, okay, then we have shown that A is the inverse of the matrix B and vice versa. B is the inverse of the matrix A. Now note that this is a square matrix that we're looking at. Okay? For a matrix to have an inverse, it must be a square matrix. Okay? But not all square matrices will have an inverse. If it does not hold this property here, then it does not have an inverse. But you must be square to have an inverse, but not all square matrices have inverses. If a matrix A has an inverse, we call A invertible or non-singular. Otherwise, it's called singular. So if a matrix does not have an inverse, we say that the matrix is singular. And again, as I can repeat, a non-square matrix will not have an inverse. Okay, so note that we see this So again, note that if I have a matrix of order Mn and the B is of order Nm and they're not equal, then I can multiply A times B because these values are the same, but I cannot multiply B times A. And so therefore, we must have a square matrix again to be able to have an inverse. Okay, but again, not all square matrices will have inverses. But if it does have an inverse, we say that that inverse is unique. So basically, a matrix will only have one, what's it called? Oh, inverse. Now, what is the procedure that we're going to use to actually find the inverse? The first example we saw, they gave us and we showed that A times B was equal to I and B times A is equal to I. But how do we actually find an inverse? What we're going to do is we're going to take the matrix A and we're going to augment it. Sorry guys, let me go back. We're going to take the matrix A and augment it with the identity matrix of the same order. So if it's a 2 by 2 matrix A, then we're looking at I2 that we're going to augment it with. And of course, we remember I2 is 1, 0, 0, 1. Okay? And then we're going to do elementary row operations as our EROs. Okay? And our goal is to put A into reduced row echelon form. Again, remember, reduced row echelon form is just the identity matrix. If we can get this this A transformed into the identity matrix, the resulting matrix that we have augmented with is our inverse. Okay? So when we're performing these ER rows, we're performing it into the entire row, including the matrix A and this identity matrix. Okay? And again, our goal is to go from A with the identity matrix, perform EROs to get it in reduced row echelon form, which is our I, and it will be augmented with A inverse. Okay? If it does not work, that means it is not invertible and does not have an inverse. Now we're going to look at this example using the rules that we used on the last slide. We want to find the inverse of this matrix A. So our first step is to form what we call a doubly augmented. So we want to find an augmented matrix. Sorry, come in here. So we write A here, and then we augment it with, in this case, I2, because we have a 2 by 2 matrix. Next, our goal is to use Gauss-Jordan elimination to put our matrix into reduced row echelon. So if we look here, we want to get this -1 to be a 0. We can do that by adding row 1 to row 2, but notice we do it for the entire row. So we would have 1 plus -1 is 0, 4 plus -3 is 1, 1 plus 1, 0 is 1, and 0 plus 1 is 1. Okay? And now, since we want this in reduced row echelon form, our goal is to now get rid of this 4. How can we do that? We can do -4 row 2 plus row 1. So that'll be 0 plus 1 is 1. This will become -4 plus 4 is 0. This will become -4 plus 1 is -3. And then we have -4 plus 0 is -4. So what we notice here is we started with, A augmented with I, and using EROs, we got our A to now be in reduced row echelon form, which is now my I. This new matrix here is now what we call our inverse matrix. Okay, so we would now need to check to make sure this is correct. So we would then do A times, well, let's write what our A inverse is. Our A inverse is -3, -4, 1, and 1. So we would need to check this by multiplying A times A inverse and make sure it equals A inverse times A, which should equal I2. I would like you to pause and do that on your own to verify that A inverse given here is indeed our inverse of the matrix. So now you should be done checking, and you will see that indeed it should work in both directions. We're now going to look at the inverse of this matrix A, a 3 by 3 matrix. To do this, we're now going to augment the matrix A with, in this case, since it's a 3 by 3, I3. So how do we do that? We would have 1, negative 1, 0, 1, 0, negative 1, 6, negative 2, negative 3. And we're going to augment this with I3, which is 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Our next step would be to perform EROs to get this part of my matrix in reduced row echelon form and turning into our I3. So we have our A augmented with I, and our goal is, of course, to get this in reduced row echelon form. To do so, we must first work with our first row, our first column, and get rid of the circled terms. Our first steps would be, we will want to do negative row 1 plus row 2, and we get this resulting line here. And then we would do, to get rid of this 6, we would do negative 6 row 1 plus row 3, and we would get this last line here. Keep in mind, we're doing it to both sides, not only the A, but also the B. So our next goal in here, that's the wrong place, please excuse me, is to get rid of this 4. Doing the operation of negative 4 row 2 plus row 3, that'll get rid of this 4 here, and we're left with 0, 0, 1, negative 2, negative 4, 1. Now, our goal is, we have it in row echelon form, is to get it into reduced row echelon form. So we first have to work with this negative 1, because we're going to go by columns. And since this is not going to affect the row, we're also going to work with this negative 1 at the same time. So to get rid of this first negative 1, which was in this position here, we can add row 2 to row 1, and we will get this resulting line here. Oh no. Okay, I think we're back now. We'll get this first line here, and then to get rid of this negative 1 here, we'll do row 3 plus row 2, and we get this resulting line here. So our last thing we need to do is get rid of this negative 1 here. And it looks like we can probably add row 3 and row 1. Adding row 3 to row 1 to get rid of this negative 1, we get this matrix here. Now what do we notice? We're left with the identity matrix. Since we were able to get our A into the identity matrix, we can say that the resulting matrix on the augmented side is A inverse. So our A inverse is equal to the matrix negative 2, negative 3, 1, negative 3, negative 3, 1, negative 2, negative 4, 1, and you can check this by multiplying A times A inverse and A inverse times A, and you should indeed get I3. So we have completed finding the inverse of this matrix A. I'm going to stop our slides here and we'll continue when we get back to class, but I would like for you to work on 8.3's homework. And I think your homework assignment, the first half of the assignment is 6 through 24 multiples of 3. So that's 6 through 24 multiples of 3. And then we'll work on that last part. I think you have after that 36 through 45. We'll work on that next week. So you're going to start with working 6 through 24 multiples of 3. And we will look at problems on the board on Monday.